It is okay now?
Yes, sir.
Yes, sir.
Okay. So, uh, so you have enjoyed the classes on electrical machines and especially electrical single phase transformer. So if I ask you, so how the two coils or two windings of a single phase transformer is designated? So what will be your answer?
Sir, it is different for a different construction of the core.
No, I am asking how the coils are.
Magnetically coupled, sir.
Now, how do we call the coils?
Winding.
High voltage winding and low voltage winding.
High voltage winding and low voltage winding. Any other answer?
So primary and
Primary and secondary. Okay. Anything else?
Sir, I think it will be high voltage and low voltage.
Yes, on high voltage and low voltage.
So somebody is saying the high voltage and low voltage, and some answer I'm getting. Primary and secondary. So we can call it primary and secondary when the transformer is in operation. So that means when we have excited the transformer. Excited the transformer means we have applied the input voltage in one coil and we are taking the output from another coil. So there we can call it primary and secondary. But otherwise, when the transformer is not in operation, in general, we have to call it as a high voltage or high tension coil and low tension coil, HT and LT coil. Okay, and in some
Yes.
transformer we don't have this difference also. Like if we have a unity ratio transformer, 1:1 transformer, that is used as an isolation transformer, we cannot call it as a primary, as a low voltage or high voltage, because you have equal trans ratio. So equal trans you have in both the winding. So there we can't say it's a high voltage or it's a low voltage. Otherwise, the coil or the winding having more number of turns is generally called the HV winding, and the coil or winding having less turns, we call it low voltage winding. Understood? So only depending on the number of turns. Okay.
Yes, sir.
Can you
Yes,
tell
sir.
me that in from one coil or one turn, sorry, from one turn, how much voltage generally we get from a transformer? If I have only
Sir,
one
root
coil,
2 pi if phi not this much voltage.
স্যার এটা তো মানে কত ভোল্টেজে অ্যাক্রস অ্যাপ্লাই করছি আর টোটাল নাম্বার অফ টার্নস লাগবে জানতে চাচ্ছি।
No, sir, तो voltage per unit turn बोलेছে।
হুম
okay,
স্যার আমার হচ্ছে এটা root 2 pi if phi not হবে।
root 2 pi
F into phi not, মানে the flux going through the limb.
Phi max. Phi max.
Yes, that is.
Okay, so that means we can think of any coil of a transformer XYZ. There may be two coils, high voltage, low voltage. There may be 3 coils, 4 coils, but the voltage that we get from a single turn is always same. It can be a high voltage coil, it can be a low voltage coil, but the voltage that we get from a single turn, that is called the ET or EMF per turn, and that also always remains same, and that is 4.44 F into phi m. Try to memorize this, because something you have to memorize. So this is called the EMF per turn. Okay, whatever be the size of the transformer, whatever may be the turns in the coil, but if we can measure the voltage of a single turn of any coil in any transformer, always you'll get this value. In any transformer. Okay,
Yes, sir.
Yes,
so
sir.
that you have to remember. Okay.
Yes.
Now, what is this F? F is the supply frequency. That means, suppose you are exciting the primary with some frequency, or for some frequency the transformer is designed. So that is the supply frequency. And what is phi m? Phi m is the maximum value of flux. Which flux? The magnetizing flux. Okay, or you can also call in this case the mutual flux. So this is the relation. Now, then how we get the primary voltage and secondary voltage? That is very easy. Or maybe some low voltage, or suppose you have a coil 1, coil 2, coil 3. So like this, suppose coil 1 is having a number of T1 turns, and this is T2 and this is T3. So you have 3 coils in a transformer. Okay, so then how you will measure this E1? So E1 will be just ET multiplied by T1. E2 will be ET multiplied by T2. E3 will be ET multiplied by T3. Okay, so this is how we can get the voltage of the exact voltage of the coil, the total coil. Okay, so you have n number of turns, n number of coils having different number of turns, but if we know what is the Mmf per turn, and if we know what is the number of turns in that particular coil, then easily we can, okay, so basically their voltage contribution is algebraically added. Got my point? Suppose from 1 turn how much voltage I am getting is a unitary method. From 1 turn how much voltage I am getting? ET. Okay. So from 2 turn, what will be the voltage? So ET plus ET, because it will be algebraically added. And for T1 number of turns, okay, so it will be added T1 times. So repeated addition means multiplication. So ET into T1, just like that. So only the thing you have to observe here, that though it is a sinusoidal quantity or a phasor quantity, but still we can add algebraically. So this thing you have to notice in this particular case. Got my point? Though it's a unitary method, but can we add just like this? Because they are the phasor quantity or vector quantity or sinusoidal quantity. I think you know what is the phasor and what is sinusoidal quantity, and how generally we add them.
Sir, I think we are taking the voltage per unit turn of all the turns are in same phase. That's why we are adding like
স্যার
algebra.
প্রত্যেকটা কয়েলের কারেন্টের ডাইরেকশন বলেছে বলে
হ্যাঁ বলো।
We are taking the RMS value of the EMF per turn.
No, it's not like that. Why it is
So they
possible? It's understood that RMS value are just
যে
adding.
ফ্লাক্সটা লিংক করছে প্রত্যেকটা কয়েলকে, স্যার
হুম।
প্রত্যেকটা টার্নকে যে ফ্লাক্সটা লিংক করছে সেটা তো সেম ডিরেকশনে রয়েছে। তো ফ্লাক্সটা যেহেতু ফ্লাক্সের ফেজটা যেহেতু যে প্রত্যেকটা টার্নের সাথে যে ইএমএফটা তার সাথে ইন অ্যাকর্ডেন্সে রয়েছে, তো সেই কারণে ডাইরেক্ট সামেশনটা পসিবল হচ্ছে।
মানে স্যার 0 ডিগ্রি হচ্ছে দুটো টার্নের মধ্যে কারেন্টের ডাইরেকশন।
Okay. So that means, suppose this is my coil, Okay, and
Yes, sir.
this from this one turn, how much voltage I am getting? I am getting ET. And how the flux is flowing? Flux is like this. This is how the flux is flowing in this code. So this is your flux. Okay, and you see one thing. So if I see this is your turn 1, this is your turn 2, this is your turn 3. So here we have considered only 3 turns. Now, if I take the axis of the first turn, and axis of the second turn, and axis of the third turn, so they are all in a same axis. Am I right?
Yes, sir.
So this type of coil is called the concentric coil. Understood? That
Yes,
means
sir.
their center, their axis are same. So this is only possible. That means this algebraic addition of their individual contributions can be possible only in case of concentric coil, because in that case all the voltages or all the voltage contributions will be in the same phase. Then only we can add them algebraically. Got my point?
Yes, sir.
Okay, so
So if
that
the
thing,
end is bent quite, then we will not be able to.
yes. Suppose just like the DC machine you have studied, na? So let me draw a coil. Okay, so suppose in a DC machine, how? So suppose this is your rotor. On that, suppose one coil you will have here, so that is A prime. Another coil you have here, that is B prime. Another coil you have here, that is C prime. Now you see that axis. What is the axis of A coil? The axis of A coil is this. This is the axis of A coil. What is the axis of B coil? Axis of B coil just perpendicular to that. So this is the axis of B coil. So that means between their axes we have some angle. Understood what I am saying?
Yes,
Yes.
sir.
This type of coil is called the distributed coil. So that is different from the concentric coil. In case of distributed coil, we can't add their individual contribution. We can't add like this. What we have to do? We have to add them vectorically.
Yes, sir.
So that means in case of transformer, it is only possible because all the coil is concentric coil. So therefore, it is possible to add them for n number, for T1 number of turns, or T2 number of turns, or T3 number of turns, as if they are piling up. So if we have ET for one coil, we will have ET1, ET into T1 for T1 number of turns. Okay. Understood? Any doubt so far? So these are very basic things, but we have to have clear concept on this, because in several times we will come across this type of situation. Is it okay?
Yes, sir,
Yes, sir.
understood.
Yes,
Okay.
sir.
Okay. So so this is about the voltage, this thing, and I've already mentioned that their voltage depends on basically the number of turns, because this ET, that is ET is constant for all this. Okay, so once we know the ET for any coil, we can find out the voltage. But ET doesn't depends on the number of turns. Mmf per turn doesn't depend on the number of turns. It is constant for all. Okay, so that means from this expression we can also write ET into T1, ET into T2. Sorry, what we can write? We can write E2 equals to E1 by T1, T2 by T2, and from that we can derive our voltage ratio expression. So that means their voltage ratio is basically their turns ratio.
Yes, sir.
Okay. So if we want to create some voltage ratio, so accordingly we have to select the number of turns. Okay, but this is the only in the related with only the number. But transformer rating is different. Transformer rating not only their voltage ratio. The transformer rating is basically its power rating. So how the transformer is rated?
KVA, sir.
KVA. Okay, so just let me know why it is not kilowatt.
Because the power factor does not depend on the power rating.
Huh?
সে পাওয়ার ফ্যাক্টরের উপর কোনো এফেক্ট হয় না ট্রান্সফরমার।
Sir, we take base voltage and base current to be the V rated and I rated, and that's why we also get the we use the KVA ratings so that we get the idea about the voltage and rated voltage and rated current.
So you just try to remember one thing. I am not explaining that in details. Generally, the rating depends on the output. Okay, so for any machine or any device, when we write the rating, this rating is as per its output, not the input. Because sometimes we will be confused where your input side is mechanical, output side is electrical. Sometimes the input side is electrical, output side is mechanical. For transformer, both sides are electrical, isn't it? You are giving electrical input, you are getting electrical output. Am I right?
Yes, sir.
Yes, sir.
Yes, sir.
And I think you have already
Yes, sir.
you have already gone through two different subjects in electrical technology, that is basic electrical engineering and electrical machines. Maybe other subjects also you have studied. So now you have some concept on electrical power. Electrical power is having the unit of VA, volt ampere. Okay, and the mechanical power is having the unit of watt. Okay, so when as we define the power up to our before coming to this engineering course, how generally did we define the power? Is a work done part time, isn't it?
Yes,
Yes,
sir.
sir.
Before joining this particular course, electrical engineering, how did you define power? Just work done part time. So that is work done part time is basically there is a mechanical power, and that is having the unit of watt or kilowatt or horsepower. Okay, but our electrical power is basically is having the unit of volt ampere, maybe kilovolt ampere, maybe megavolt ampere, kV or MVA or VA. So that you should remember. Now any device which is having the output side is electrical, like like an alternator. Now alternator, what is the input? Input is mechanical and output is electrical. So how the alternator should be rated? With VA or kilowatt?
VA.
Yes, sir.
VA, because I've already mentioned the output. As per the output, the rating is specified. Now, if I think of a motor where we have input side, what is the input side?
Electrical.
Electrical. And output side?
Mechanical.
Mechanical.
Electrical, sir. Mechanical.
For motor, the output side is electrical or mechanical?
Sir, mechanical.
Mechanical. So how the motor will be rated?
Kilo.
আরপিএম এ তো করে, মানে আউটপুটের দিকটা তো আমি দেখবো।
পাওয়ার বলছে
Is all rating is always the power rating. Okay, so speed also is some another parameter, but the power is basically decide the size of the machine. Anyway, so it will be rated for kilowatt or watt. Okay, so what if you see any motor's nameplate, then you will find watt or kilowatt or horsepower. So all are having mechanical unit, that is watt. Now we have also another analogy to this mechanical power in our electrical, and that is called the average power or active power. Okay, the power which we call the mechanical power in our electrical analogy, we call it as a active power or average power. In general, we call it average power, but with sinusoidal assumption, we call it active power. Okay, so those I think all those things you have already exposed to. Okay. Now, so I think you have understood the KVA thing. So that means as the VA is involved here, the apparent power is involved here. So the voltage doesn't decide everything in a transformer, isn't it? What else we need? We need current, because the VA is basically the product of voltage and current. Am I right?
Yes, sir.
Yes, sir.
So that means we have to think of current.
Yes, sir.
Okay. Now you see, suppose we have some input current, some output current relation. So that we have already studied. Okay, so how this output and input currents are related? So that also you have to think. Now, unlike the voltage, so if we have a voltage at the primary side, definitely we'll get some voltage at the secondary side. But in case of current, so if we don't have a current in the secondary side, but still we'll have some current in the primary side. Am I right? So that is the difference with the voltage.
Yes, sir.
Okay, so that means if we don't have any current in the secondary side, but still we'll have some current in the primary side. What is that current?
So no load current.
Magnetizing. Yes, sir.
Okay, so that is the no load current, I0. And that is the summation of, or rather vector summation of, the magnetizing current and a loss component of current. So we should know this relation, isn't it? So I think you all know this. So this Im is the magnetizing current and Ic is the core loss of component of current. So why it is required? Because suppose you don't have the other coil, you have only one coil. Got my point? Suppose in a transformer core, you have only one coil. Then what will be the current?
Can you repeat?
Suppose in a transformer, I have removed the second coil. The coil which is being excited, that is the only coil which is on the core. We have removed the other coil. Then what will be the current drawn by this coil when I am exciting by its rated voltage?
No load current.
So এই কারেন্টটাই হবে IM plus I.
Voltage
So
by
this current only it will flow through the coil.
IM plus IC.
So that means this current, no load current, is not related to the other coil. Then who decides this no load current then?
So কোরের উপর ডিপেন্ড করবে।
Correct. It depends on the material. Okay. It depends on the material, core material. Okay, so both this magnitude of this
Sir,
magnetizing
Will
current
it
and
depend on?
yes,
Sir,
and
will
also
it depend?
bolo?
Sir, will it depend on the dimension of the core or only the component of the core?
It will depend on the yes. No, it will depends on the material. Okay, so that is the BH characteristics, BH curve.
Okay, sir.
Also anyway, also the how the core is formed, whether it is laminated or non-laminated, and how much voltage you have applied. What is the frequency of that coil or of this excitation voltage? So all will decide because the voltage, the frequency, okay, all these will decide the magnetizing component IM, and all this BH characteristics. What is the area under the BH loop, and how the core is formed, whether it is laminated or non-laminated. All these will decide the value of IC. But anyway, so this current is not related to the other coil. Okay, so that you have to understand. So if we have only one coil, then also we'll get this current. So that means we have an inductor. So one coil means if we remove the other coil, so it will be just an inductor. Okay, so and this inductor will draw some current, and that is the I naught. Okay, but whether the same current will be drawn if I have a positive or some finite value of I2.
No,
Will it
sir.
be the same current?
No,
No,
sir.
sir. The current will
It
be
increases.
More, sir.
So it will be increased.
Yes, sir.
The I1 current will increase. Now why it will increase?
So due to the current flowing in the secondary side, the flux will change in the core and the
Just a minute.
will violate.
Just a minute. হ্যাঁ বলো।
So if the secondary current flows, then the flux through the secondary coil will increase. But as the Lenz's law, the flux going through the limb cannot change radically. So another compensating current will flow through the primary side in order to kill the flux generated in the secondary side. That's why the current will increase in the primary side and net current will increase according to.
Hello.
Yes, sir. Hello, sir.
Okay, so one thing you have missed. What is that?
Sir,
Hmm.
so when load
Mutual
is
coupling, there will be also a current in the primary side.
so when
Yes.
the load is connected across the secondary, current flows in the secondary winding, which opposes the primary flux
Yes.
and tries to reduce the overall flux.
Hello.
But yes, sir. Hello.
বলো তাড়াতাড়ি একটা ক্লাসে আছে বলো তাড়াতাড়ি হ্যাঁ হ্যাঁ I'm just getting interrupted by a phone call. Okay, continue.
Sir, should I continue?
Yes,
Sir?
yes, yes. Continue.
Sir, I am saying that on the secondary side, when a current will flow, it will increase the flux through the secondary coil. And as the Lenz's law says that flux cannot change radically, so a compensating current will generate in the primary side in order to kill the secondary flux. The secondary flux that is generated due to the
No, Lenz's
load.
law is not saying that.
Sir, can I say try?
Yes.
Sir, when any load is connected across the secondary current flows, which opposes the primary flux and tries to reduce the overall flux. But from EMF equation, we know that the flux is constant as long as that V by F is constant, frequency and V by F. So flux should not depend on the load. Hence, hence the core flux should be same at the load as well as at no load. Therefore, there should be a compensating current to compensate the lowering of the flux.
Okay, one vital point you were missing. Anyway, you see
when
one
you-
thing. So
Sir,
your this thing is okay, but when there will be a current.
Sir, can I try, sir?
Yes.
Sir, when there is a load attached, sir, there will be a resistive drop. So due to which the voltage, sir, secondary voltage will decrease. So, sir, because the power is constant, sir, therefore the current will be there will be a current in the primary side.
Resistive drop.
Yes,
Not
not resistive, sir, inductive also in the secondary side due to the load.
Now you see one thing you have told correctly, that is if there is a current in the secondary, if there is a finite current in the secondary, so one thing you are missing, that is who generates the flux. It is not the current that generates the flux, that produces the flux. So there your basic concept is wrong. It is not the current which generates the flux. It is the MMF that generates the flux. Okay, so this is the secondary MMF which is generated just after having a finite I2, finite secondary current. And this generates the flux because the flux is MMF by reluctance. I think you have also studied the magnetic circuits in very basic electrical engineering.
Yes,
Isn't
yes,
it? So that means once there is a current in the secondary, first thing that we get is the MMF, magnetomotive force, like electromotive force or voltage in an electrical circuit. In a magnetic circuit, we need some MMF to produce some flux. So not only the MMF decides the flux, but also the value of the reluctance or the permeability of the material, because reluctance is inversely proportional to the permeability. Am I right?
yes, sir.
Yes, sir.
So that decides the value of flux. So that you are missing. The main thing, that is the MMF. Now the question is, the phi2 will be generated by the newly formed MMF, but in which direction? That is given by the Lentz's law. Okay, so always the result, always try to oppose its initial or its root cause. Okay, the result always try to oppose its root cause. So what is the root cause here?
N1
I1, N1, I1.
Not N1 I1 directly. The root cause is phi 1, because you see
Yes, sir. Yes, sir.
why this I2 is generated. First, why this phi 2 is generated? Phi 2 is generated due to I2, this MMF N2 I2. Why this N2 I2 is generated? Due to I2. Why this I2 is generated? Due to E2. And why this E2 is generated? Due to phi, magnetizing flux. So what is the root cause of this? This is the root cause you have to find out, and that will be opposed by phi 2. Or the root cause is the magnetizing flux. So it will try to reduce the magnetizing flux.
So can you please repeat this part?
Okay. Now you have understood how the phi 2 is generated. Now how this phi 2 is generated? Phi 2 is generated. What is the immediate cause of that? The MMF. The secondary MMF. Sorry, N2 I2 I have to write. The secondary MMF is the immediate cause. Right? Now, how this secondary MMF is generated? Secondary MMF is generated because previously also there is some number of turns, but there was not MMF. Why this MMF is generated? Because there is a current in the secondary coil. So I2. So I2 is the immediate cause of this MMF. Now, how this I2 is flown to the circuit? Because of this E2 voltage in the secondary coil, isn't it?
Yes.
Now, who is generating this E2? You just find out the expression of E2. E2 is 4.44 F phi m into N2. So that means what is the variable which is responsible for E2? That is phi m. So that means what is the root cause of this phi 2? The root cause is phi m. So therefore the phi 2 will try to oppose phi m. Okay. So
Yes,
have you understood? Now, if it tries to oppose the phi m, so phi m will try to reduce. As simple as that. Right? So if it acts in opposition of phi m, so definitely the phi m will try to reduce. So 4.44 F phi m into T1. So if the phi m is reduced, who will reduce? The E1 will reduce.
Yes, sir.
Now you think of the primary circuit. In the primary circuit, what you have? You have V1 and you have E1. So this difference is producing the current as per as a simple voltage equation. This potential difference is producing the primary current.
Yes, sir.
So if in this is reduced, what will be the difference? Difference will increase.
Increase, sir. Yes, sir.
So if this difference will increase, definitely your current will increase.
Yes.
So it's very simple. Why the current? I'm not assuming anything. Okay, so this is how the current will increase. Now the question is, where the game will end?
So যখন balance হয়ে যাবে দুটো flux.
Because everywhere there should be some stable point. There will be some equilibrium. When this equilibrium will be reached, so that we have to understand. The equilibrium will be reached when the root cause of this disturbance will be nullified. Got my point? So who is the root cause of this disturbance? Root cause of this disturbance is this MMF. When it will be nullified by the primary current, the game will end and we will have an equilibrium point. And that equilibrium point is basically N1 I1 equals to N2 I2. So that you have to say, because this is called the MMF balance in a transformer. Okay, so this will give you the equilibrium point, equilibrium condition.
Sir, in
So-
the previous point, I have, sir, one doubt, sir.
Yes.
Sir, when you so you told that V1 minus C1 will decrease. Suppose that two batteries are connected, having different values, then current will current flow through it if it is short circuited, sir. Then how can we say that if E1 is reduced, then current will flow through the where short?
No, if we have two voltages having equal voltage, okay, so then there will be no current. But if there is any difference in this battery voltages, definitely there will be some current.
Okay, sir.
Isn't it? I got your question. You are saying that suppose I have a battery. This is a 5-volt battery, another 5-volt battery I have like this. So there will be no current. So the current will be zero. Absolutely zero, because the source voltage are exactly equal. But if there is some perturbation in this voltage, so definitely there will be some finite current.
But sir, the magnitude of the current cannot be decided earlier. If the voltage is reduced.
The magnitude of this current will be decided by the source voltage itself. So how much perturbation is there in the other voltage source? So how much it is getting reduced? So it will be decided by that, because the current is always follow this rule, the potential difference. So V1 minus V2 by some impedance or resistance. If there is some potential difference, then only the current will flow. Na? If there is no potential difference, the current will not flow.
Okay, sir.
Got it? Oh.
Yes, sir.
Yes, sir.
Okay, so I think you have understood. This is the very important point. There is the MMF balance. So that you have to understand. Okay, because yes.
Sir, don't know why I have logged in to this meeting with a different name, sir. My name is Kvl Goswami. I don't know why I have joined with a different name, sir. A problem occurs. I think my name is Kvl Goswami, sir. Please take the attendance of my.
Okay, so I'm taking 5 minutes time from you, because the rules I have not told you. A rule of attending this class is you have to rename yourself properly, and the naming format should have the last 4 digits of your roll number, then underscore, then your name. Okay, so that is how you have to rename yourself. So everyone has to rename yourself. To rename yourself, you have to go to the participant list in the Zoom, and then you just mouse over on your name. You just find out your name in the participant list and mouse over on that. You will get more option. In that more option, you will get a rename option. From that, you just try to rename yourself, just like everybody already started their renaming. Okay. Then it will be easier to take the attendance. Huh?
ল্যাটেরালদের ক্ষেত্রে কি করব স্যার?
Lateralদের ক্ষেত্রে the same thing, only first letter will be L. L 4 digits underscore number.
ওকে
So every day you'll do this thing at the very beginning so that I can take the attendance, and I will authorize our seer. Who is the seer? Soinik. Okay. Soinik should take this pen to take the attendance and maintain the attendance in some extent. Okay, so you take a screenshot for the timing. You just take the screenshot and try to maintain the attendance. So who is Shiv Shankar Das? Shiv Shankar Das. What kind of the roll number it is? 0200. Is he a
Yes, sir.
repeated candidate?
No, sir. Is 002012.
No, last 4 digit of your roll number.
Sorry, sir. Yes, sir. Sorry.
পল্লব সরকার, রাহুল বিশ্বাস, রায়ন দাস, রৌনক হাসান, সায়ন্তন সিংহ, সোহম সাহা, সৌম্য বাসুরি, অরিত্র হালদার. You try to rename yourself quickly. I know you are present, but okay, Mohan Bormon, you try to see the naming format of other students, your other classmates, and try to rename in that format. Mohan Bormon. অরিত্র হালদার, সৌম্য বাসুরি, সোহম সাহা. Still you didn't rename yourself. And Animesh. Who is this Animesh? I don't think these people are there in the class. Animesh, unmute yourself. Animesh. অরিত্র হালদার. অরিত্র হালদার. সৌম্য বাসুরি. Am I audible? Soinik?
Yes,
Yes, sir.
Yes, sir, you are audible.
Why these people are not responding? That means they are not in the class. They are logged in virtually. They are present virtually. পল্লব সরকার, রাহুল বিশ্বাস, রৌনক হাসান. Are you there in the class? If you are in the class, you quickly rename yourself. Otherwise, I will not give you attendance.
Yes, sir. I am present. I am present, sir.
But why you are not renaming yourself? As I told you.
স্যার আমার নাম তো পুরোটাই আছে টাইটেল সহকারে।
আরে স্যার যেভাবে বললেন সেভাবে কর নেমটা।
স্যার আমার নেট একটু
বললো তো রোল নাম্বারে লাস্ট 4টে ডিজিট দিয়ে তারপর আন্ডারস্কোর তারপর তোর নাম।
Okay, so let's start again. So I think you have understood how the MMF balance we have in a transformer. Okay, so that means after this MMF balance, additional current which is flowing in the primary coil, that is I1, but initially already we have this I0. So that means now the current will be increased, isn't it? And that is another KCL equation, another current equation. Can you see the whiteboard? Can you see the paint screen?
Yes,
Yes,
sir.
sir. Yes, sir.
Okay. So that means
স্যার আমি সৌম্য অ্যাকচুয়ালি স্যার আমি একটু নিচে গেছিলাম মা ডাকছিল তখন সেই জন্য শুনতে পাইনি।
রিনেম, তোমার নামটা রিনেম করো, যে ফরম্যাটে দেওয়া আছে সেই ফরম্যাটে রিনেম করো, বলেছি।
আচ্ছা স্যার।
So that the net primary current will be different from the previous case, because previous case there was only I0 current. Now it will be I0 plus I1. Got my point? So that means we got equations like this. So this is one equation we got. This is another equation. Okay. What else we have for a transformer? What are the other equations? Other equations are the KVL equations. I'm just writing down a KVL equation. I think you all know this KVL equation. So these are all current equations or KCL equations that you have written, like equation number 1 and equation number 2. But the KCL equation or the KVL equations or voltage equation will be like this. So E2 minus I2 R2, okay, minus JI2 XL2. So this is another equation, that is the secondary KVL equation, and the primary KVL equation will be E1 plus I1 R1 plus JI1 XL1. So try to jot down all this equation and try to remember this. So this equation number 3 and 4 have the units of volts, whereas the equation number 1 and 2 have the units of ampere. So therefore the equation number 1 and 2 is called the KCL equation, and 3 and 4 I call it as KVL equation. Okay.
Yes, sir.
Understood?
Yes, sir.
Okay. So what else? So these are the equation, basic equation, and other equation already we have. You have, that is the that MMF balance equation and the voltage ratio equation. So we can also name them like this. This is the 5, equation number 5, and this is equation number 6. Okay. And this also you can write the equation number 7. The Mmf Pattern. So only these equations you have to remember for a transformer. Then it will be easier for you, because once when you will draw the equivalent circuit diagram, or when you will draw the phasor diagram, all these equation will be required. All the equation will be needed. So you try to remember these equations. So that means what we have? We have 2 current equations, 2 voltage equations, 1 MMF balance equation, 1 voltage ratio equation, and the very basic equation, equation number 7, that is the Mmf Pattern equation. ওকে
স্যার একবার নিচে স্যার ওই স্যার আমার ডাউট আছে স্যার স্যার বলছি ওই ইকুয়েশন যেটা লিখেছেন স্যার I1 ওটা ড্যাশ ইকুয়াল টু I0 প্লাস I1 নাম্বার 2 ইকুয়েশনটা,
নাম্বার 2 ইকুয়েশনটা কোনটা?
তো এটা
হ্যাঁ
I1 লেফট সাইড স্যার এইচে স্যার I1 ড্যাশ আছে তো
হ্যাঁ I1 ড্যাশ আছে।
স্যার ওইটা
বলো।
স্যার ভি স্যার নাম্বার 4 ইকুয়েশন স্যার I1 ড্যাশ হবে না?
কারেক্ট। Yes, that will be net primary current. Okay. Acha, one thing I'm just asking you, can you draw a circuit as per the equation number 4? You just try to draw a circuit as per equation number 4. Suppose you have the equation and you have to draw the circuit. Can you draw?
So it will be a series combination of resistance and inductor. And the applied voltage will be V1.
You just draw and show me by sharing the screen. I'm giving the permission. So you just quickly draw it and show me by sharing the screen. So all you try, and randomly I will ask you.
স্যার আমি আসলে ফোনে ক্লাস করছি, শো করবো কি করে?
হ্যাঁ ফোনে
স্যার রাখবো কোথায় স্যার?
খাতায় আঁকবে।
তারপর ক্যামেরা অন
হ্যাঁ
করে শো করবো?
হ্যাঁ ক্যামেরা অন করে
ওকে স্যার।
ওকে স্যার।
flip the camera towards your notebook and show me. করেছো? কে দেখাচ্ছ বলো? I will spotlight him.
So can I?
Shall I show?
Who? Shayon or
Yes,
Vivo?
sir.
Shayon. Okay.
I also go.
Okay,
Will I
Shayon.
show?
I'm just spotlighting Shayon. Just a minute. But your video is not there, no?
Yes, sir.
Have you switched on
Shall
your
I
video?
turn on my video?
Yes,
No,
yes.
sir.
Otherwise, how can I see that?
I will share screen, sir. Means I
Okay,
have
sure. Okay, you just
drawn
share
it.
the screen. No issue, but somebody asking that. Okay, so you just share the screen. Oh, why you have written E1 like that? E1 just like a voltage that is like the V1.
Yes, sir. Yes, sir.
Why
Yes,
you
sir. I
have
note
write
this.
the voltage, the potential, the voltage we can just show by this plus minus.
Okay, sir. So this coil is not required.
This coil is not required.
Yes, sir. I just showed the primary.
Who told you that that is a coil?
Okay, sir.
That is
I
just
see.
a voltage.
Yes, sir. Yes, sir.
The element you have only resistance and reactance.
Yes, sir.
Okay, so it's okay. So stop share. Then I'll draw the same thing. So that means so he has drawn like this. So this as per the equation number 4. KVL equation number 4. So this is the V1 and this is the E1, and current flows like this, and this current should be I1 prime, I1 dash, and this resistance will be R1, and this reactance should be XL1, leakage reactance. Okay.
Sir, can we represent the E1 with a voltage source or something like that?
Yes, but now it is not required. It is okay. As for the polarity also you can mention, just like he has mentioned, that also you can. Okay, so now you try to figure out the equation mentioned in 2. Equation number 2 you try to draw quickly. It's a KCL equation. That means you have to find out a node from where you have to show 2 currents are outgoing, 1 currents are incoming. Previously it was a loop. I think you have all understood this is a loop. So which is given by the equation number 4. But for equation number 2 it will be a node because it's a KCL equation.
Yes, sir, done.
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 Okay. Who will show me? Vibhor?
Yes, sir.
Will you show by screen sharing or?
Yes, sir. Yes, sir. I will show by screen sharing.
Okay, dekho.
Yes, sir. Yes.
All you try. Why others are silent?
Sir, is it visible, sir?
It's coming, not yet done.
Sir, is it?
হ্যাঁ না তাহলে কারেন্টটা কোথায় গেল? আমি এটা তো
Yes,
হোয়াটসঅ্যাপ
sir, I'm sending the picture actually, sir.
but that you have to know that you have to incorporate. No, it's not correct. I think that you have to incorporate with the existing circuit. And a previous circuit with the previous circuit you have to add this.
Oh, okay, sir. I
Yes.
think it is different.
কে দেখাবে?
Can I show?
হ্যাঁ stop share করো. Okay, now we'll show Ritik.
I can present. Yes, sir.
Yes, screen sharing or just okay. No, it's wrong.
Can I show?
Because you see what is the problem here. I don't know why you have drawn this branch. I don't have this branch as per the equation number 2.
Sir, here is one IM. So you only mentioned to use only equation 2.
Equation number 2. Just after the equation number 4, you have to add equation number 2 in the circuit.
Then, sir, I could only incorporate only a impedance here.
No, you don't have to incorporate anything. Only you have to draw the branches. And that is also after I1 prime, not I1.
Yes, sir. I1 prime.
No, but through the R1 and XL1, I1 prime current will flow. But in your circuit, through R1 and XL1, I1 current is flowing. It is wrong. Got my point?
Sir, I have taken the net current as I1 dash.
But through R1 and XL1, what is the current flowing? It is I1. Is it I1
Yes,
or
sir.
I1 prime?
Yes, sir. It is I1 prime.
Then your circuit is wrong.
Sir, will the parallel branch be after the R1 and XL1?
Parallel branch, I don't know what is parallel branch. That we'll all find out.
Sir, can I
You
screen share?
suppose you don't know anything about the transformer, you forget everything on the transformer. Only you just try to visualize these equations. That's all. এই ইকুয়েশন গুলোকে আমরা ভিজুয়ালাইজ করছি, realize করছি, circuit realization. This is called the circuit realization. Okay.
Yes, sir.
So that means from this we have two branches, because here what is the current is incoming I1 prime. Now I1 prime is bifurcated and it is giving two branches. One is having I1 current and another is having I0. You see, this is the equation number 2, isn't it? So this is the node. যে নোডের আমি কথা বলছিলাম, so this is the node. This node you have to realize. Got it? So this is the node you have to realize, and you have to realize two branches. One carries I1, another carries I0. So two outgoing current and one incoming current. Incoming current is I1 prime and outgoing currents are I0 and I1. Next, you have to realize equation number 1. Equation number 1. Similarly, equation number 1, I0 is incoming. And what are the two outgoing currents? Outgoing currents are
IM
IM
and IC.
and IC.
Yes, sir.
Okay. So how would you draw now this IM? So how will complete this circuit then?
স্যার আই নটটা যেটা ছিল ওটার দুটো কম্পোনেন্ট হবে আইসি আর আইএম, মানে ইন প্যারালাল।
স্যার আইসিটা স্যার কি একটা, স্যার আইসিটা রেজিস্টার দিয়ে পাস করব আর একটা আইএমটা স্যার
আইএমটা হচ্ছে ম্যাগনেটাইজিং
Inductor.
কম্পোনেন্ট, ইন্ডাক্টর।
হ্যাঁ স্যার, হ্যাঁ
I don't know how it is flowing this. What is E1? So we get E1 across something, na? So what is E1?
Sir, E1 is the voltage difference across the coil.
Now what is E1? E1 is 4.44
Yes, sir.
F
sir.
IM as per the equation number 7, na?
N1. N1, sir.
Yes. So this is your E1. Okay. So how actually we got this equation? Do you know? E1 equals to minus am I right? Ultimately, we get this E1, capital E1 equation from this equation. This is a very basic equation of as per the Faraday's law of induction. Am I right?
Yes, sir.
Yes,
So
sir.
this
Yes,
is
sir.
nothing but E1 d phi m dim dt. Mathematically, we write that. You just revise your mathematical knowledge, derivative. Can you
Yes,
write
sir.
this?
Yes, sir.
Okay, so this is nothing but the inductance. The definition of inductance is this. So this is the magnetizing inductance, L di dt. So this is how the N d phi dt and L di dt equations are similar. And if we represent that in frequency domain or steady state domain, what we get minus x lm into capital IM. So that means the E1 is basically a voltage drop across XLM, which is basically a reactance. So it should be a J. Not LM, you can write just M. The L you can omit because it's the mutual inductance. So across this, actually you are getting this E1 voltage. Have you understood this? No.
Yes, sir.
Let me know whether you have understood. Here I have skipped something, assuming that you know all this.
Sir, can you explain it once more?
Okay. So I think you all know this expression E1 equals to N d phi dt minus T1 d phi
Yes,
dt.
sir. Yes, sir.
And what is this? Why I am writing this T1 a forme কেন লিখলাম? Because I want to represent in terms of L di dt, not N d phi dt. So N d phi dt and L di dt is similar. Only the representations are different. When we represent some voltage as a source, then we try to represent it as N d phi dt. But when we try to represent that voltage as a voltage drop, then we draw the analogy of inductance. So it's an LDI dt. So LDI dt is basically a voltage drop. So therefore this negative sign is coming. Okay, so that means ultimately E1 equals to L di dt. And what is that L? That L, now for that actually you should know the definition of inductance. So this should be clear to you. What is inductance? Inductance, L, is defined as psi by I. Okay,
sir.
so what is psi? Psi is the flux linkage, not flux.
Yes.
Flux linkage. Or we can write N phi, or here we are representing T. So T phi, number of turns into phi by I. So in differential term, so we can write T d phi dt, where T is the number of turns. So this is how we define an inductance.
Yes, sir.
So I think you know this definition, or if you don't know, you just try to remember this definition. Inductance is rate of change of flux linkage with respect to current. Psi by I. Now psi is basically the number of turns into flux by I. In differential term, it is T d phi di. So that definition I have put here. And why I am written Lm? Because this inductance and the inductance which I have drawn here, they are different. Why different? Because you see, just try to understand this point. It's very important. Suppose when I am exciting a coil, okay. Now this coil, suppose primary coil I have excited by some V1 voltage. Now through this coil, some current is flowing, that is I naught. Okay. Now this I naught will then generate an MMF. What is that MMF? What is that?
I1 into N1.
Okay. So T1 into I naught. So that MMF will be generated.
Yes, sir.
Okay. Now this MMF will try to produce some flux. Earlier also I told you that MMF is responsible for generating the flux. So this will generate some flux. Now this flux, whatever the flux generated by this MMF, it will have two components. Why two components? Because one component is very obedient. Like you who are attending the class regularly. They are very much obedient. Why? Because they have provided a channel, have been provided a channel. Through that channel, they will flow. Like you, I have provided you a option. You have a class and you are attending the class, but there will be some flux which is not obedient like you, and always they will try to skip the class. So here also, in case of magnetic circuit, the MMF which is generated T1 I naught will produce some flux. Some flux will flow through the core, and some flux will not flow through the core. The flux which is flowing through the core, I can term as phi m, and some flux which is not flowing through the core, I am calling as phi L. So leakage flux and mutual flux.
Yes, sir.
Okay, now this mutual flux is basically depends on one component of I naught, that is phi m only, and leakage flux depends on the whole value of I naught.
Yes, sir.
Okay, so therefore the ratio of T1 phi m by Im is basically the Lm, and the ratio of T1 phi L by I naught is basically the leakage inductance. So here comes two things. One is the mutual inductance, another is the leakage inductance. Okay, got my point? So one is the first is the mutual inductance, and second one is the leakage inductance.
Yes, sir.
So that we have to understand two things. So always there will be two things. I cannot expect that all the students will be obedient. All the student will regularly attend the class. There will be some leakage student who will always try to skip the class, try to bunk the class in case of physical or virtual. Okay, always there will be a percentage of student who will not try to flow through the channel. So here the thing is similar. But anyway, but by proper design, we can minimize the leakage flux, we can increase the mutual flux. That is different issue. Okay, so that means the voltage E1, we can think of the voltage drop across inductance Lm. Okay, so across Lm as if there is a voltage drop E1. So therefore I have drawn like. Okay, and this core loss, if I if I discuss the loss, core loss in details, then also you'll find out your core loss also depends on the voltage, not the current. So therefore, this core loss, for that I will take is a responsible. Okay, so this is also you can represent like this: E1 equals to some IC square into RC. These are all fictitious resistance and fictitious current. Remember, so this I am just assuming like that. This IC, you cannot measure IC directly, you cannot measure RC directly. It's just not just a normal resistance or current. Okay, so as if there is a resistance RC, as if through which a current is flowing IC, sorry. So therefore, you have the voltage drop, and the core loss is this. So these two things you have to add with the previous equation, 7 equations. The concept of this inductances and the concept of this core loss of resistance RC. So these two concepts you have to add with your previous equations, 7 equations. আগে যে 7টা ইকুয়েশন বললাম তার সাথে এই দুটো কনসেপ্ট অ্যাড করতে হবে, ডেফিনেশন অফ ইন্ডাকটেন্স and the concept of core loss. Okay, so understood. So what is left? So we got E1. So that is equation number 4, 2, 1. So can you represent equation number 3 quickly? It's just similar to the first equation, that is the equation number 4. So I am just giving it, I am just showing it for you. So
সেমই হবে,
same
তাহলে কি
হবে, but
under-
এখানে it will be like this. Here the input side will be different. Input side will be E1 and output side will be V2. Am I right?
Yes, sir.
So that will be the change on. In the primary, the input side was V1 and the output side was E1. Here the input side will be E2 and the output side will be V2. So that will be the only change. And the current will be I2. So this is your E1. This is your V1. This is your E2 and this is your. Okay, so the first circuit is called the primary equivalent circuit and the second circuit is called the secondary equivalent circuit. This is not the equivalent circuit of a transformer. Remember, these two circuit is not an equivalent circuit of the transformer. Equivalent circuit of a transformer will be a single circuit in which both the primary and secondary parameters and variable will be represented. Here the first circuit is the primary equivalent circuit and the secondary and the second circuit is the secondary equivalent circuit. Okay, so to get the exact equivalent circuit of a transformer, what we have to do? Any idea?
Sir, we have to refer one side to the other, any one side.
I don't know how to refer. Now,
chance ratio দিয়ে refer করলে
now I don't know. Now you just see, can we connect the circuit 1 and circuit 2? মানে সার্কিট 1 এর সার্কিট 1 এর হ্যাঁ সেটা হবে না তাই না, সার্কিট 1 এর লেফট টার্মিনাল দুটো আর সার্কিট সার্কিট the left terminal of the circuit 2 and the right terminal of the circuit 1, can we connect? No, because the voltage differences are there. There will be huge short circuit, right? Just a few minutes back, somebody pointed out that there is a potential difference. It's not possible. Now, currents are also different. In one branch, it is I1 current, another branch, it is I2 current. So it is not possible.
Yes.
Okay. So how can it be possible? Mathematically, can we do something? Physically, it is not possible. So mathematically, can we do something?
Yes, sir. Sir, if we convert this E2 to E1 by some operation.
Yes, mathematically, you try to do that. So that means I will write once again this equation, that is V2 equals to E2 minus equation number 3. I'm just writing again I2 XL2 minus, sorry, একটা টার্ম মিস করে গেলাম, I2 R2. Okay, what you will do, you just multiply both the sides by N1 by N2. N1 by N2 V2, N1 by N2, not N1 by N2. For you, it will be T1 by T2. So don't change the nomenclature, otherwise it will be problematic for me. So both the sides, I'm just multiplying by the turns ratio. Let's see what we'll get. Is it okay?
Yes, sir.
Yes.
Okay. Now you just tell me what is the unit of this?
Volt.
Volts per turn.
No, it's volts only because T1 by T2 doesn't have any ratio. That it doesn't have any unit because it's a ratio. So it's just another voltage. So we can write that another voltage. This is a scaled version of the previous voltage. So I am writing V2 prime. Now what is this component?
This
Are you
will be-
familiar with this?
Yes, sir. This will be E1.
Yes, you try to exploit another equation, that is equation number 5. So if we use equation number 5, we will get it is E1. Okay. Now another equation is left which we have never used. What is that? The equation number 6.
Yes, sir.
Yes, Mmf equation.
So what is the expression of I2? I2 equals to T1 by T2 into I1.
I1 T1 by
So already there was a T1 by T2, but if we substitute I2 in terms of I1, another T1 by T2 will get.
Yes, sir.
Am I right?
Yes, sir.
Yes, sir.
Remember, I don't know what do you mean by referring. But I can do all these things mathematically. So this is your V2 prime equals to E1. Okay. Now J I1. Now here I have T1 by T2 square into XL2. What is the unit of that? T1 by T2 square
So same as
into
impedance.
XL2. So can we write
Yes, sir.
XL2 prime?
Yes, sir.
Yes, sir.
Yes, sir. Yes.
Similarly, here also I can write R2 prime.
Yes, sir.
Okay. Now, if we have this, so this is basically the same equation number 3, but it's a modified version.
So now we can compare this equation.
Yes. No, I will not compare. What I will do, once again, I will try to draw the circuit, or I will go for the circuit realization. What will be the circuit realization? Here I have E1. Here I have new resistance. Previously it was R2, but now it is R2 prime. And this is the new reactance XL2 prime. And here I have a different voltage, V2 prime. So this is the new circuit realization. So we can say it 3A, and this is corresponding to your 3A. Now you see this 3A, now you can connect directly with the circuit number 1. If this is the circuit 1, and if this is circuit 2, so this 3A circuit, you directly connect with circuit number 1, am I right? You see the voltages are same. Voltages are E1, currents are I1. Here also in this circuit, currents are I1, current I have not drawn. So currents are I1, Okay. So that means directly we can connect with that.
Yes, sir.
So if I connect that directly, then we will have a single circuit, and that is called the exact equivalent circuit of a transformer. Okay, so let me draw quickly because I don't have any time. So already it is. So all the basic, from the basic principles, I don't know what are the standard terminology is used. Only from the basic this thing I am drawing this. So here you have E1. Here the current I0. Here this is I1. Here this is I1 prime. Here it is IC. Here it is IM. Here it is V2 prime. And here it is V1. Okay.
Yes,
So
sir.
what it is called? Once again, it is called the exact equivalent circuit of a two-winding single-phase transformer. Don't miss any term. Huh? It is an exact equivalent circuit of a two-winding, because there is a single winding auto transformer. I am not considering that. For that, you will have a different equivalent circuit. This is the exact equivalent circuit of a two-winding single-phase transformer, where we have modified the secondary KVL, secondary equations, or it is called the secondary parameter referred to the primary. Okay. Now, if I try to the opposite one, opposite thing, then we have to modify other three equations. That means equation 1, 2, and 4. Then it will be called primary parameter referred to the secondary. Better to use this because here I have to modify only one equation, equation number 3 only.
Yes, sir. Less number of parameters.
Yes, sir.
Understood? So all these
Yes,
you have
sir.
studied in earlier class. Only I have just recapitulating today for you so that you can brush it up quickly.
So then the voltage difference across the node where the from where the I0 is coming out and the zero voltage line is E1 then.
Where is E1 only? The E1 I have shown, na?
Yes, sir. Okay.
E1 is this node voltage. You can say this node voltage is E1. E1 you can say the voltage across the magnetizing reactance XM, or the voltage across RC. Everything is E1.
Yes, sir. Yes, sir.
E1 is the midpoint voltage, induced voltage. But how you can measure E1 from this circuit? Practically, is it possible to, because it's a midpoint voltage. E1 is not accessible from the terminals. From the terminals, only V1 and V2 prime is accessible, or V1 and V2 is accessible. How can you measure E1 then?
So from the
The
concept of voltage
resistance
regulation.
inductance.
Yes.
স্যার কারেন্টটা বার করে ভোল্টেজটা বার করে যদি টোটাল ইম্পিডেন্স দিয়ে যোগ করে
No. It's just you make V2 0. Not sorry, V2 0, not I2 0. I2 makes 0. That will give you I1 0.
Yes.
Now I1 টা 0 হলে তো হয়ে গেল। So there will be no voltage drop in that part. That means the whole
Sir, only
voltage.
I0 will cause the.
Yes, sir.
So that is called the no load test. No load. At the no load, you can measure, because in that case your terminal voltage V2 prime will be 1. Okay. So that way you can measure. So anyway, all these things you just try to recapitulate. I will share this video. If you have any question, you can ask me
I have a
quickly.
question.
Yes.
Yes, sir. I have a question. Sir, যেটা leakage reactance হবে.
Yes.
Yes, sir. So that we can find means leakage. What can I say? Leakage, that inductance we can find out by MMF by that leakage. Sorry, sir. Leakage flux that can be calculated by MMF, like N1 into I1 dash by reluctance. Sir, how to find out the reluctance of that path? Means for a magnetic core we can do like L by mean length by mu naught into area of cross section of the core.
There
But
is
for
a air
here, how
leakage
can we
reluctance.
measure yes, sir. How can we measure that reluctance? Means how will we decide that one?
No, that is that air cap. You have to find out how much distance is there through which this air this flowing. Actually, this analytical way, if you try to measure, it is very difficult. Generally, we use finite element methods for that. It's a complicated one because it is a distributed one, because it will be different for different turns. Okay. So and for every turn it will, that the contribution will change. So it is analytically, if you try to find out, it will be difficult. So what we do, we generally do some test. By that we try to predict this is the leakage inductance, not analytically. That means not by these expressions. Got my point? Just like you see, if you try to measure this core loss component of current IC, practically there is no current IC. So if you connect an ammeter and if you try to find out what is IC, never you will get that. Then how this IC is measured? IC is measured in the indirect way. Why? Because you see, there is no current IC, because through the core, what is the current flowing? Is it IC? কোরের মধ্যে থেকে আইসি কারেন্টটা ফ্লো করছে? It's not that. No, কোরের মধ্যে তো আইএম কারেন্টটা ফ্লো করছে না। কোরের মধ্যে দিয়ে যে কারেন্টটা ফ্লো করছে, that is IE, eddy current. But that is a different current. I am not going into the details of that current. Okay, but this IC current is not that which is flowing through the core. Okay, then how this IC current is measured? IC current is measured from the no load test. How? Because from the no load test, the ammeter reading directly gives you the no load current. Am I right? From the no load test, the ammeter current, it directly represents the no load current, ammeter reading. Okay, and from other two readings, that means the voltmeter and wattmeter reading, you can estimate what is the value of no load power factor. Got my point? And from that expression, I naught cos phi is your IC.
Yes, sir.
And I naught sin phi is your IM. So this is how indirectly you are measuring. But if you try to measure directly what is IC by some ammeter, you will not find out what is IC, because actually IC current doesn't flow. Okay, we try to visualize that IC in our circuit, equivalent circuit, because there is no equivalent circuit. You see, the equivalent circuit, you are showing there is no electrical isolation. If you see the electrical equivalent circuit of a single phase transformer, it doesn't have any electrical isolation, isn't it? That means it is electrically connected. But the main feature of a two-ending transformer is an electrical isolation. If you have studied auto transformer, the main disadvantage of an auto transformer is it is not electrically isolated. So in some application, only to give the isolation transformer is used. So that is called the isolation transformer. It doesn't have any trans ratio. It doesn't step up or step down voltages. Okay, so that means you just think what is the importance of giving isolation. But you see, from this equivalent circuit, we are not getting any isolation. Then what is the use of this equivalent circuit? The equivalent circuit, because you see, when you will go for a power system, there will be 1,000 transformers, 1,000 generators in a power systems. So every time if you deal with two circuits and all these 7 to 9 equations, it will be difficult for you. So what we do, we make a single circuit representation. Only it represents all the mathematical equations of a transformer. Exactly. So therefore it's called the exact equivalent. And sometimes we make an approximation of this. How? Sometimes we remove the shunt branch totally. By that, what we do, we reduce the complexity of the problem. Because if there is 1,000 number of transformers, now if we have 6 elements like this, you see here we have 6 elements, 3 resistances and 3 reactances. Now if we remove the shunt branch, then you will have only 1 resistance and 1 reactance. Your problem will be reduced, your complexity of the problem will be reduced manifold. So therefore, in most of the cases, we go for an approximate equivalent circuit, not the exact equivalent circuit. I think you have studied all this. Got my point?
Yes, sir.
So all these
Yes, sir, yes.
are to reduce our problems or complexity of problems. সবসময় যদি আমরা দুটো আইসোলেটেড সার্কিটকে স্টাডি করতে চাই, so it will be difficult. Okay.
Yes, sir. Question ছিল।
বলছে একটা কোশ্চেন আছে যে স্যার ধরুন আমাদের কাছে ক্যালকুলেশনের স্টার্টিং এ আমাদের কাছে প্রাইমারি সার্কিটের রিঅ্যাকট্যান্স আর ইম্পিডেন্সটা अवेलेबल রেজিস্ট্যান্সটা अवेलेबल আছে, কিন্তু সেকেন্ডারি সার্কিটের কোনো প্যারামিটারগুলো अवेलेबल নেই। তাহলে স্যার ইকুইভ্যালেন্ট সার্কিটে আইডিয়াটা কিভাবে জেনারেট হবে যে R2 ড্যাশ আর XL2 ড্যাশের ভ্যালুটা মানে কি রকম হবে?
R1 and R2 prime will have similar range. XL1 and XL2 prime will have similar range. That means if we say R1 is 0.1 ohm, R2 prime also will be 0.1 ohm. XL1, if it is 1 ohm, then XL2 prime also will be 1 ohm. Just like that. They are in the similar range, but not R2, not XL2. When we refer the parameters in one side, then their value comes in the same range. বুঝতে পেরেছো? যখন আমরা রেফার করি তখন ভ্যালুগুলো সেম রেঞ্জে আসে, মানে R1 এর সাথে R2 প্রাইমের রিলেশন আছে, মানে সেম রেঞ্জে আছে, কিন্তু R1 R2 there is a huge difference.
মানে কিন্তু স্যার এই R1 আর R2 ড্যাশের মধ্যে মানে এই রিলেশনটা কিভাবে আসছে, মানে স্যার রেঞ্জটা কিভাবে ইকুইভ্যালেন্ট হচ্ছে?
By multiplying the this trans ratio square. You see, okay, so today I don't have any time. Okay, so I can discuss. You just give me 5 minutes. Suppose the primary is low voltage and secondary is high voltage. This is a step up transformer. Okay. Now, what do you think? So the resistance that you will get for the primary and resistance you will get for the secondary, will they be same? Different. Which will be more?
Sir, low voltage side, the current will be higher, so lower resistance will be required.
No, lower resistance. So the high voltage resistance will be less, will be more, na?
Yes, sir.
Yes, sir. High voltage resistance will be more. Yes,
and low voltage resistance will be less. So how will you ensure practically that? And practically তুমি কিভাবে সেটা এনশিওর করেছো? you have made higher number of turns in the high voltage coil. So if higher number of turns means the wear that you have used for the high voltage coil is the longer than the low voltage coil.
Yes, sir.
So that means if I write the formula for R, rho L by A, so this L for HB is more. And what about the area? You know that for high voltage coil, there will be less current will be passing. Because voltage is high means current will be low. So for low current, you don't need higher cross section. The cross section you can reduce.
Yes, sir.
Okay, so this is how you are ensuring high value of resistance. Got my point? Whereas
Yes,
for low voltage side, so that means the value of resistance is decided during the design itself. যখন আমরা ট্রান্সফরমার ডিজাইন করেছি তখন then we have designed the high voltage coil, a thin coil, okay, less cross section coil having more number of turns or longer wear. And for low voltage coil, as it has to carry more amount of current, I have kept is a larger cross section and it is having less number of turns. That means the length will be less. So that means the resistance of the low voltage coil will be less. So that is there is a difference in their values, nominal values. So R1 and R2 are completely different in this case. Now, from the design itself, if we try to relate that, then we will find out that R1 and R2, their values are related by their trans ratio, the trans ratio square. যখন আমরা ডিজাইন করেছি তখনই যদি আমরা দুটোর ভ্যালু কম্পেয়ার করি মানে দুটো ভ্যালু রেশিও করি দেখবো the ratio that we will get will be their trans ratio square. So that means
impedance matching যেটা করে.
Yes, that means if I multiply the R2 with T1 by T2 square, we'll get the similar value of R1. Okay, understood?
Yes, sir. Yes, sir.
Okay. So any more question? Okay, so thank you very much.
Thank you, sir.
For attending the class and good night.
Thank you, sir.
We have the next class.